So let us start this, okay? Just pay keen attention now. All right, the acidity of organic compounds. Now, we must be able to explain the difference in acidity of alcohols, phenols, and carboxylic acids. We must be able to understand the difference in acidity between alcohols and phenols in terms of the overlap of atomic orbitals and stability of the alkoxide and phenoxide ions. That is what we must understand. That is what we're here for. All right? Now, before we move any further, I will give you guys a full breakdown of the conjugative effect, or what we call resonance. Because if we don't understand it, this topic is going nowhere. Okay? So, let's look at this. The conjugative effect. It occurs within molecules containing multiple bonds, such as those characterized by the alternating double and single bonds, as seen as benzene, right? So we know that this is because of the pi orbital overlap and creation of a delocalized system of pi electrons, right? We know this, increasing or enhancing the stability of the molecular structures. Okay? This doesn't only occur within benzene and other aromatic compounds, right? Well, it doesn't only occur in benzene. Let me not say that. It occurs in carbonate ions and carboxylate ions, which are also aromatic in nature. Your carboxylic acids, right, and your carbonates, right? They are also aromatic in nature, because guess what? sp2 hybridized carbon, all right? sp2 hybridized carbon. Well, yeah, sp2 hybridized carbon. It is flat, right? All of these different things. It has a characteristics and it is aromatic. Okay. So just looking at the aromatics of benzene, they're using our toluene, or what we call our methyl benzene there. We can clearly see alternating double bonds and single bonds, and the movement of electrons participating in the delocalized system in enhancing the stability of the molecule. Okay? So everybody can see that and everybody understands, right?
Yeah.
Yes, sir.
All right. This is what we have here now. On the top we have ions and on the bottom we have ions. What is on the top? What type of ion is on the top? Is it the carbonate or the carboxylate?
Carbonate, sir.
All right, CO3 2 negative. All right, so that's a carbonate. So the carbonate has a alternating bond, as you can see, right? So bond alternation, right? Really simple bond alternation. All right, so the reason why these electrons continue moving throughout these systems, creating resonance systems, is because we are trying to reach stability. Stability is the formation, right, of a species, or basically, you could be the same species, right, in a state of the least amount of energy. High energy systems or high energy species can be described by charge, right? So if charge is localized onto one area of the molecule, it is of high energy, right? So since molecules always try to find the lowest energy state possible, they try to delocalize that charge, right? So the electrons continue to move across everything within the system in order to delocalize the charge, to make sure that the charge is not centralized on one specific atom, and that is how it tries to stabilize the molecule. Okay? So the analogy that I tend to use is two friends walking up a hill. One of them, let's say that they're carrying bricks, right? Or yeah, bricks. One of them has bricks in his or her hand and the other doesn't have any. All right? So that will create a system of high frustration, because you're going to complain, oh, why are you carrying all the weight, right? And the other person is not carrying any, right? So I think of it like that, as a high frustration situation, right? Right? So if it is one brick, you can actually share the weight, right? So you carry some part of the way, and the other person carries some part of the way. So it's basically something like that for molecules. This carbon, right? This oxygen bears a negative charge for some time, right? And then the electrons move over, creating a double bond, and no, it no longer has that negative formal charge. So it's something like that. Each element bears the formal charge, right, in a high energy state, right? But it is eventually shared. It is eventually delocalized as electrons continue to move, right? So this is just a representation, right? A good representation of how it works, right? It isn't exactly how it works though, but this is how we explain it and how we are able to represent it in chemistry. Okay? So looking at the lower part of it now, right? Oh, let me just let everybody know unit 1 is actually over. So let me just text the unit 1 group. Give me a moment, guys. Yes, still part. The meeting is open, but unit 1 actually ended.
So this is unit 2.
Yes, it is.
Okay, I'll just stay for.
Okay, no problem. All right, so on the lower end of the spectrum now, we're not, well, on the lower half of the screen now, we're actually looking at the carbonate, right? So the carbonate, we can find them in carboxylic acids, right? And instead of we having a three center system, in this case we have 1, 2, 3 oxygen, a three center system in which electrons travel around these three centers, right? We actually have a two center system, 1, 2. So the electrons travel between these two centers, right? So it's the same type of friend analogy. They're sharing the charge. So in one case, oxygen 2 has a charge. In the other case, oxygen 1 has a charge, and they continue to shift back in these resonance states, right? But really and truly, they exist in a state between, right? So they exist in a state between, and we use a dotted line to show that resonance. So we give both oxygens the single bond they need, right? And then show the double bonds existing between both oxygens, right? Using that dotted line. Everybody's fine so far? You guys would have looked at this before, no? Go ahead.
No, not really, sir.
Not really.
So
Go ahead. What's the question?
I'm not really sure what the question is, but are you saying that because it could go through these different states, you just consider this one at the bottom?
Okay, so it's not okay. So remember what I said, right? So it's not actually how it works per se, but this is how we are able to visualize it in chemistry, right? So in chemistry, right, in our working diagrams, we can see, sorry about that, the two systems working, right? So the two different resonance structures of the carbonate, right? 1 and 2, right? But really and truly in nature, the double bond exists somewhere in between, or the electrons exist somewhere in between both oxygens. So we denote that by the dotted line from one oxygen leading to the other oxygen, instead of having to write it in one specific resonance structure, if you understand what I'm saying. It's kind of like where you have the benzene ring. Cause we know the benzene ring, you can write it in two different structures. So you'd have the benzene ring like this, and you can draw it in another alternating pattern. But we tend to just draw in benzene ring using the circle in the middle, right? Showing that it's alternation happening. So it's similar to that we have there. Okay.
Oh yeah, I think I got this, sir. Thanks.
All right, no problem. Okay, so if there are any questions, you guys can just stop me, right? So the conjugative effect, specifically the oxygen atom, is more negative or electronegative than the carbon atom, right? So we're looking at that specifically, right? Or the hydrogen atoms within these molecules, right? In this case, we're talking about this, well, dare I say hydrocarbon, because this is not a hydrocarbon, right? But in this carboxylic acid, right? So the bonding pairs of the electrons tend to move towards atoms, right? shown in the image there, right? So it tends to move towards more electronegative atoms, right? So this bond itself, right, that we see here, the hydroxyl bond, right, or the OH bond here, the electrons actually move closer to the oxygen, right? And in the carbon itself, the electrons are actually not moving to the carbon specifically, but moving in the direction of the next oxygen up here. Okay? So we're looking at that. So the carboxylate ion forms and exists as a resonance hybrid, right? So two extreme forms. As we said, two extreme forms here. So it exists in these two extreme forms, right? And it's relatively stable in this type of form, right? When the hydrogen ion is gone, right? When the substance, right, is reduced, right? Yeah, when it's reduced in this type of way, right? So what we're seeing is that when the hydrogen is left, right, or when the hydrogen leaves specifically, we actually have the formation of a stable species, right? And we know it's stable because anything that is aromatic or anything that shows conjugative or resonance effects, right, is stable. And the stability of these ions, right, or the stability of the conjugate bases of these acids are imperative in understanding the acidity. It's something that we need to definitely know. All right. So that's really the
Sorry, could you
conjugative
just
effect.
repeat that statement again? Just repeat the statement.
The stability of the conjugate bases of our organic acids are important in understanding the acidity of our organic compounds.
Okay, thank you.
All right. So the inductive effect is actually slightly easier to understand. All right. So it's really the charge position within a molecule. Right. It's really polarity from unit one. Right. So groups of atoms can influence distribution of electrons around a specific atom, such as carbon atoms specifically, by either attracting or withdrawing electrons. And this phenomenon is known as the inductive effect. Everybody has generally heard of intramolecular forces, right? So everybody's heard of that, and the fact that a more electronegative component tends to drag electrons closer to it, creating a polar substance, right? Everybody understands that from structure, right? Not structure. Types of bonding. Everybody would have understood that from Unit One, right? The creation of a polar compound, because one element is more electronegative, it drags the electrons closer to itself, creating a pole.
Yes, sir.
All right, so remember that specifically. So bonds between atoms of different electronegative activities, right? The electronegativities become polarized due to the variance in electronegativity, right? So something like hydrogen versus something like chlorine have vastly different electronegativities, right? Therefore, they will form a polarized molecule. This polarization is symbolized by an arrow directed towards the more electronegative atom, right? So atoms or groups possessing greater electronegativity than carbon tend to withdraw electrons from the vicinity of the carbon atom, resulting in the negative inductive effect. Right? So let's look at this. For instance, this. It does look a bit cloudy. Right? So you can see what we call a negative inductive effect here. So it's negative inductive here. Why is my pen deciding not to pen at the moment? Right, so it's a negative inductive effect for the carbon versus a positive inductive effect for the chlorine. Right? So it's positive inductive effect for the chlorine because electrons are moving towards the chlorine. And it's negative inductive effect for the carbon because they're moving away from the carbon. Okay? So it's as simple as that. So you can see that electrons move throughout the molecules themselves, right, or the compounds themselves, right, due to differences in electronegativity. All right? Are there any issues or any complaints so far?
No, sir.
All right, everything seems lovely. All right, as we say, it's Unit 1 stuff. All right, So it's supposed to be bigger than it. Okay? So it's really just that. It helps in our understanding of the stability of the different alkyl groups as well. So atoms are groups less electronegative than carbon tend to donate electrons to the carbon atom. Alright? Usually alkyl groups are electron donating groups. And groups containing nitrogen, fluorine, or oxygen, right, or any other halogens or chalcogens tend to be electron withdrawing groups. Alright? So we have those things. The halogens are group 18, the chalcogens are group 17, right? So those two groups, any substituent containing those tend to be electron withdrawing groups, right? And anything with a lower, electronegativity than carbon, right? Usually other carbon atoms or hydrogen atoms tend to be electron donating groups. Hopefully that makes sense. So the polarization is represented by the arrow pointing towards the more electronegative atoms. So in this case, the R groups or the alkyl groups are less electronegative. So the electrons move towards the positively charged carbon within the carbocation. Right? I think at this level we don't look at carbon ions, but we look at carbocations only, I think. Alright, so really as simple as that. And we saw this already. Alright, so this is a tertiary carbocation, then a secondary carbocation, then a primary carbocation. Hopefully everybody saw that. And we know the stability of all of them because we discussed Markov-Nikov's effects and stuff like that before. Okay? So let us have a move on. So let's get into the topic. Let the topic begin. Because once we have an understanding of the inductive effect and the conjugative effect, then we'll be able to understand the topic at hand. Alright? Comparing the acidities of these compounds. The solubility of ethanol, ethanoic acid, and phenol is important to understand. So ethanol and ethanoic acid are soluble in water, right? They can form extensive hydrogen bonding in water. We do understand that. We do know that. We do love that. We do adore that. Alright? Phenol is only sparingly soluble in water and is solid at room temperature. And this is because it has a higher molar mass, right? And it has a large aryl ring. Right, so it is an arene. Arenes are not normally that soluble, right? Especially phenol, right? So it kind of reduces its capability to form these hydrogen bonds. Okay. So looking at this now, the acidity of the compounds with the OH groups. So the pKa values, right, for some compounds containing the OH groups, and the lower the value of the pKa, we know the more acidic the compound is, right? So looking at these, which would be the most acidic of all of them?
Ethanoic acid, sir.
Not the yawn. Ethanoic acid, right? So ethanoic acid, then we would have our phenol, then ethanol specifically, alright? So ethanol is a weak acid, phenol is a weak acid, ethanoic acid is a weak acid, but in organic chemistry, we stopped talking about inorganic chemistry a long time ago. That is done business, right? In organic chemistry, our strong acid is our ethanoic acids, right? Or not our ethanoic acid, our carboxylic acids rather, right? We're just using the simplest forms to explain the acidity. Because once we know that we're increasing the alkyl ring or the alkyl groups on these to propyl, butyl, octyl, it wouldn't make any sense, right? Once you understand this, the foundation of the topic, you can understand every other derivative. Make sense? All right.
Yes, sir.
Lovely. So, some of this information, all right, got from my beloved chemistry teacher, the best of the best. All right. So, I'm going to make sure that I make reference to her. So, the structure of phenoxide, right? We have to talk about the structure of phenoxide, the structure of these different things. In organic chemistry, we always talk about structure, and structure is how we understand everything. So, phenol itself is a very weak acid, as we saw before. Its pKa is only what? 10? 10. Alright? So we have that there. So it ionizes slightly in water to form a phenoxide ion. So we know what weak acids are, right? We do know what those are. I think we do. Hopefully we do know what weak acids are, right? So phenol is a much weaker acid than ethanoic acid, but is more acidic than water or ethanol, right? And we're gonna figure out why that is. And in aqueous solution, the pH is just below 7. Alcohol and water appear to be neutral, right? So it is too weak to actually liberate CO2, right, from the carbonate specifically, right? However, ethanoic acid can liberate CO2, and phenol neutralizes sodium hydroxide, but neither ethanol or water will. So it's showing you how acidic phenol is, right? It's acidic, but it's not that acidic. Right? So there are some things it can do as an acid, and there are some things it can't do as an acid. Okay? So it's a very weak acid. So looking at the structure of phenol here, right? So the phenoxide ion, right? So we know that phenol is a hydroxybenzene derivative, right? Therefore, with these phenoxide ions, we know that the hydrogen is now released into solution, and this is how the resonance of the system helps to stabilize the phenoxide ion. Okay? So within the phenol itself, it tends to stabilize electrons around the ortho and para positions, and this is why the OH group tends to be orthopara directing, as we looked at in the last topic, right? So it tends to stabilize electrons around there, and even when it is ionized, it stabilizes electrons around there as well. So those are the most stable areas, right? So this is just showing the stability or how resonance is able to stabilize the phenoxide ion. Alright? So the phenoxide ion is actually really, really stable. It's really, really fine. Alright? So the more stable, we're gonna talk about the stability actually. Let me not bring in all the different types of, proportionalities, directly proportional, inverse proportional, all those type of stuff yet. Alright, we're just understanding it first. Are there any questions so far though? Any questions? Going once? Going twice? Alright. The structure of an ethoxide now. Ethoxide is basically the same thing as just any alcohol that has lost its proton. Right? So this is just ethoxide. So these are all the alk oxides, right? Specifically for alcohol derivatives for the conjugate base of the alcohol, right? So this is a conjugate base of ethanol, okay? What we call N-ethanol, regular ethanol. Because if you change the group to create a positional isomer, it won't work, right? Because anywhere you put the OH group, it will still be N-ethanol, alright? So it would still be N-ethoxide, okay? And for the structure of the carboxylate, right, we have there our ethanoate ion, right? We are more familiar with the ethanoates, I believe, all right? These are things that help to find to define our or esters, all right? So we have this here. Note that the ethanoate will actually exist in its resonance stability, right? Its stabilized form in between those two double bonds there, because the double bonds would actually shift, right? So it will exist in that state between, right? But this is only showing one extreme, okay? So it's resonance stabilized here. So note, ethanoate is resonance stabilized, ethoxide isn't, and phenoxide is resonance stabilized. Does that have any bearing on this? This resonance stabilized, this is not resonance stabilized. Have a look at it. The stability of the conjugate base has a role in the acidity of the substance. Keep that in mind. Okay? So let's look at this. The differences in acidity of ethanol, phenol, and ethanoic acid, right? So let's have a look at this. Ethanol specifically, the charge of any ethanoate ions formed is concentrated on that one oxygen. Alright? Not only is it concentrating on the oxygen, but it is getting more charge based on the inductive effect, right? So it's also gaining a positive inductive effect from the ethyl group, as oxygen is the most electronegative atom, right, in the entire substance. So we can see that here. The oxygen already bears a charge, a negative charge, plus more electrons are moving towards it, right? So there's no resonance stabilization here to decrease that charge there. This increase in negative charge on the oxygen atom, right? This increases negative charge on the oxygen atom as we see there, right? So anytime we have an ethoxide ion being created, right? We actually have the ethoxide ion existing in such an unstable state, it is more likely to reaccept the hydrogen and stay an alcohol. So what we can say is that the equilibrium position of this dissociation exists to the left, and that defines a weak acid. What you learned in module 2 of unit 1 chemistry, acid-base equilibria. If the equilibrium of the entire expression exists to the left, it is in favor of the reactants, right? And that is what's happening for ethanol. And because it's a weak acid, it exists in an irreversible reaction itself, right? So it is reversible. There's no conjugative effect to stabilize the ethoxide ion at all, right? There's no carbonyl group. Carbonyl groups usually are able to create aromatic aliphatic, well, not really aromatic aliphatic compounds, but it's really aromatic compounds for straight chain stuff, right? So you have aliphatic versus aromatic, but let's say that cyclic versus acyclic compounds, right? The carbonyl group is usually how we have resonance stability in acyclic compounds, right? If you're not understanding the terminology I'm using, let me know. Let me know. But what's basically happening here is that all the charge is being stabilized, is being held by the oxygen, plus it is being added more pressure, or more pressure is being added, right, by the alkyl groups, which posit a positive inductive effect on the oxygen, right, making such an unstable conjugate base that it is more likely for it to actually reaccept the hydrogen to become the alcohol. So the resonance structure doesn't exist. The inductive effect is actually not helping it, plus it already has a negative charge. Right? So listen this carefully. The stability of the conjugate base determines the strength of the acid. The stability of the conjugate base determines the strength of the acid. These are things that you would have probably gotten from unit 1. Alright? But if you haven't gotten it from unit 1, you need to get it now. Alright? The stability of the conjugate base determines the strength of the acid. Or it is a determinant, right? So it helps to determine the strength of the acid. Let's put helps to determine the strength of the acid, right? The position of this equilibrium is so far over to the left, ethanol exists as an undissociated molecule with hardly any ethoxide ions existing in solution, right? So it's something like this. Everybody's fine so far with ethanol? I've ranted on for too long on this slide. Any questions? Please, if there's a question, I don't care what question it is, ask the question, so we can clear up any misconceptions. Let me give you guys some time to just reread or come up with questions. Any issues?
Yes, sir. Sorry, but can you explain why ethanol having a double O bond contributes to it not stabilizing?
Okay, a double, well, you mean a carbonyl bond? Oh, you said a carbonyl bond, yes. Okay, so if it had a carbonyl bond, it will not be an alcohol, alright? So if it was actually an ethanoic acid, because that's what it would actually be, it would be able to resonance stabilize itself, right? So remember how the carboxylate works, right? This is the carboxylate. So if it had a carbonyl group, it would allow the relationship between it and the stabilized, well, not the stabilized, the centralized charge on the oxygen, right? And this charge could actually be dampened out. So resonance can occur when you have a carbonyl group. Alcohols don't have carbonyl groups. So you're just gonna have to live with the centralized charge on your oxygen. Plus, your alkyl group will be contributing electrons to your oxygen as well, making it even more unstable. Make sense?
Sir, can you go over the part of the alkyl group?
The alkyl group. Remember, the inductive effect states, right, that within a compound specifically, if you have something that is more electronegative, everything else that is less electronegative will start to contribute electrons towards it. So what's happening here is that the oxygen itself already has a negative charge, as you can see, right? Plus all the carbons and hydrogens will be pushing its electrons, right, onto the oxygen. Or rather, the oxygen has higher electronegativity, means it has a higher tendency to attract electrons. So it will be dragging electrons across the molecule towards itself, making itself more unstable.
Oh, yeah, that's sir. Thanks.
All right. Any other questions? All right, moving on. So phenols now. All right. So these slides, Jay and Thomas, we love Miss Thomas. All right. So this information is so clear, I didn't even want to change information. All right. This is just good. All right. So phenols now, in a phenoxide ion, one of the lone pairs of electrons in the p orbital on the oxygen atom overlaps with the delocalized electrons in the phenol ring. As a result, the extended delocalized system is formed, and it includes the oxygen specifically. So if you look at this here, right, we have that system like that. Okay, we can see that. We can see the sp, let me see, 1 2 sp3 hybridized oxygen lies upon hell. Lies from the pit. Is that sp? That kind of sp. Yeah, it's sp3. Right, so it's sp3 hybridized. Let me actually check something, to make sure that I'm not lying. That is sp2 hybridized. Okay, so I have sp2 hybridized oxygen here, right, existing by itself, having all of its fun with its hybridized p orbital sticking out. All right, but because the p orbitals are so close to the p orbital system of the ring, it actually lends for overlapping, right? So the ring itself actually overlaps with the p orbitals, right? The top and the bottom. So what starts happening here? The resonance effect specifically is increased because the delocalized electrons can now move over a larger area. Interesting. Remember that we have now an extended delocalized system. The delocalized system now took in another p orbital. It is now extended. Therefore, it is increasing the resonance effect, right? Allowing more area for the delocalized electrons to now move over. There's also extra delocalization, right? So the extra delocalization reduces electron density on the oxygen, because not what we're seeing here is that the extra electrons on the oxygen now are now participating within the ring. Because once orbitals overlap, the electrons can exist within the orbital itself, the orbital system. So electrons that the lone pairs that exist on oxygen are now participating within the ring. Hope you guys can see that. The charge is spread over the whole ion rather than being confined to oxygen, and this is what makes phenol more stable or more acidic than ethanol, because once you find a phenoxide ion, right, the phenoxide ion stabilizes the oxygen way more than the ethoxide is able to do. The stability of the ions can tell you the acidity of the acid. Alright? The stability of a conjugate base tells you the acidity or the strength of the conjugate acid. Phenol is way stronger, right? Well, not really way stronger. It's like 6 magnitudes higher, right? But it's stronger than ethanol because it has a resonance structure, because it has a benzene ring, because the free electrons on the oxygen itself, right? And ultimately the free electrons that will amount after the hydrogen disappears, right, will now participate in the ring, increasing resonance structure or the resonance effect specifically, right? Making the substance, the phenoxide ion, more stable than the ethoxide ion. And this is why phenols are more acidic than ethanols. Make sense? Phenols are more acidic than alcohols, and this is why. Any questions? I'm legit making sure that I take every minute to kind of wait and wonder if you have questions. Let me check the chat real quick. Alright, I don't see anything in the chat. So drop a 1 in the chat if you're ready to move on. If you are not ready to move on, please ask a question. Seems like nobody's ready to move on, but nobody has a question. Are there any issues in the chat? Go ahead.
So initially, what makes the hydrogen be liberated? Is it the positive inductive effect you get from the oxygen? So remember, initially you have the phenol, the OH. I will not say the bond the polar, but what exactly made the hydrogen have the ability to be removed from that to form the phenoxide ion?
Alright, so watch me creating aromatic ester. Alright, so we have this happening, yes? We're
Yes, sir.
seeing what actually results in the removal.
Yeah.
Dissociation. The fact that if it's sparingly soluble, but when it is solved, right? When it is dissolved, right? Things tend to dissociate, right? It could all be a nucleophile or something in the solution, right? That drags the hydrogen away, right? But we're just looking at it being dissolved, right? It is a probability. Some of them will not dissolve, some of them will dissolve. So it's a mere fact that the hydrogen can dissolve because in water, we have hydroxides. So it could be a hydroxide leading it away, right, with its free electrons, resulting in an electrophilic attack of our poor hydrogen. And since the bond is already weakened by the electronegativity of the oxygen, the hydrogen might leave, creating a phenoxide. So something like that may occur, leaving us with a phenoxide. Alright? But what's happening here is that because of the resonance ring, by the way, this is just denoting a ring, by the way. Just saying. Alright? By the entire resonance ring thing, these electrons can't participate within the ring. They can actually go within the ring. So resonance can actually stabilize the molecule. So it's not as needy for the hydrogen. It's not as needy. It is actually stable on its own. It's fine. It can live on its own. It doesn't need any hydrogen to live on its own. All right? It's fine for the most part because it's still a really, really terrible acid. So in relation to ethanol specifically, it's better than ethanol. It's more independent than ethanol. Ethanol needs that hydrogen to stay alive. The ethoxide ion needs that hydrogen to be stable. It is most definitely unstable without it. But the phenoxide, no, it can exist without hydrogen for a while. It's fine. So what we see here is that the equilibrium position lies further to the right for phenols than for ethanol. Make sense? Come on, it's supposed to make sense, man. Principles of chemical equilibrium?
Yes, sir. Makes sense.
Yeah, man. Okay. Alright. Let's actually principle these things. that I think a lot of person urge you guys to learn from Unit 1 because you will need it in Unit 2. This is exactly what I would say. Alright, so chemical equilibrium, you guys need to know those. Okay? So the phenoxide here, right? So it's even more information chatting on about the phenoxide. Right? And I basically spoke about this, so it should be fine. The stability of the phenoxide is important. And notice that we have a negative inductive effect on the oxygen, right? Because the electrons can participate in the ring because of the overlapping of the ring system onto the p orbitals of the oxygen. Okay? So we should remember that, okay? So let's look at ethanoic acid now. This is the last acid that we have to look at, right? Or do we? Okay, so some of the p electrons in the COO group, right, are delocalized. This delocalization reduces electron density on the oxygen, right, specifically, right? And we're speaking about the oxygen that lost the hydrogen, right? The oxygen from the hydroxyl group. The conjugative effect stabilizes the ethanoate ion specifically, right? So the conjugative effect is greater, right, than in phenol. And this is why the stabilization is greater. And this is why ethanoic acid is more acidic than the phenol because its resonance effect is greater. Okay? The position of the equilibrium is further to the right than compared with ethanol. Not, well, ethanol and phenol, right? But it's further to the right than phenol. Therefore, it will be further to the right than ethanol. Right? The hydrogen ions are not as strongly attracted to the ethanoate ion. So the ethanoate ion is least likely or less likely to form undissociated molecules than is the phenoxide ion. And here we can see the sp2 hybridized. I think this is sp. Wait, this is sp. sp2 hybridized thing, right? So we have this here. So sp2 hybridized oxygen. This. So within the phenol itself, right? This would be overlapping with the ring. These two will be overlapping with the ring, right? And within the ethanoate, right? Those two will be overlapping with carbon, right? And overlapping with the other oxygen. So this is what's happening within the ethanoate ion. So in this case now, right? After we have the loss of the hydrogen specifically, we have this type of resonance system existing over three different centers, both oxygens and the carbon. Alright? So the two p electrons, which normally overlap sideways to form a pi bond, right, will actually, well, overlap in that specific way, right, and allow electrons to move freely around that system. Right? So that's how we actually show double bonds being created and formed, as the p orbitals continue to overlap and stop their overlap, right? So they start to overlap and de-overlap constantly, right? But we generally just say that they form this entire system of overlap, this entire system of resonance, something that I love to call a resonance system over the molecule itself, destabilizing the charge, right? Or delocalizing the charge rather. So this is what we have happening here. So it's actually much stronger in ethanoate rather than in phenol. You can read the slide if you want. It is nothing but helpful information. And while I wait, are there any questions? Resonance will be all over this topic. So if you don't understand resonance, oh boy. Boy, do I have news for you. But any information you need, it's your duty to go and get it, alright? So that is really it. That is it. That is it for the acidity of our organic compounds. Phenols exhibit weak acidity, right? Surpassing that of ethanol or water. Phenols demonstrate the lower acidity levels compared to carboxylic acids. The acidic nature of phenols arises from the charge delocalization of the phenoxide ion facilitated by the delocalized electrons in the phenol ring. Unlike alkoxides, for example, ethyl oxide ion, right? The zero atom, the oxygen atom in phenol lacks the localized charge. Alright? Consequently, it readily accepts hydrogen ions to form a molecule. So you can talk about all those type of things, but I will know if you truly understand once you get your surprise. Just open your present, have a look at your questions, and see whether or not you can answer them. Alright? Go ahead.